Washington State University. Go Cougs!
Hi there. Welcome to the presentation on task parallelism. My name is Ananth Kalyanaraman. I'm a faculty in computer science at the School of Electrical Engineering and Computer Science in Washington State University. So today I'll be going over some fundamental concepts about task parallelism and also discuss a real-world use case that arises in the context of activity prediction. So let's get started. There are primarily two forms of parallelism. One is called data parallelism and the other one is task parallelism. So sometimes it's easy to harvest parallelism from the virtue of the fact that we have multiple tasks that need to be executed, and perhaps many of those tasks can be executed concurrently. So this is what we refer to as task parallelism. Contrast this to where you have parallelism or concurrency that emerges from the virtue of the fact that we have a large volume of data and you can distribute the data across parallel machines and have basically the parallel machines concurrently execute the same task on those different pieces of data. And that version is what is called data parallelism. So for this lecture, we will primarily focus on task parallelism. So here is a very quick example. So let us say there is a faculty and there are 15 questions and 300 exams, meaning 300 students who took the exam. And the faculty has to grade all these 300 exams. So there are two ways to possibly break the task of grading all these 300 exams. One way is basically assuming that we have 3 TAs to help out. One way is to take the 300 exams and distribute equal number of exams to each of the 3 TAs. So that would be 100 exams per TA. So this is a data parallelism. That's because the TAs are grading different exams, but they are performing the same task on each of those exams, which is to basically grade the entire exam. There is also another way of generating parallelism for the same grading task. So that is to assign the TAs, the 3 TAs, different questions as opposed to different exams. So for example, TA1 might get questions 1 through 5, TA2 might get questions 6 to 10, and TA3 may get questions 11 through 5. So these are two alternative ways or strategies that we can deploy to parallelize the task of grading. And we will be focusing on task parallelism, which is to really focus on how different tasks can be performed by different computers in a parallel setting. So as you could have rightly imagined by now, there are a few challenges that we have to deal with when we look at task parallelism. So the main challenge that arises is because of the dependency between tasks. Let's call this inter-task dependency. So for example, there are two tasks that are shown on the right. Think of these as two functions in your code. And task number one basically writes onto a variable called A, and that variable is used by task number 2. And so this generates a dependency from task 1 to task 2. In other words, this line of your code in task 1, which writes onto A, has to complete before you can execute the line of code that uses the value of A. And so how do we negotiate this dependency? Because dependencies generate challenges during parallelism. If one task has to wait for the other task to complete, we have in effect sequentialized the process or serialized the process. And hence the concurrency that we have in terms of the resources is unfortunately not reflected in how the tasks are computed. Note that this kind of dependency may or may not really show up when you actually execute the program, because it's very much possible that this assignment into A that's happening in task 1 is sitting inside an if statement or a control statement. And if that condition is not even satisfied, then this line of code may not execute at all, and which means really that this value of A is not really going to be needed by task 2. But there's no way to really predict this. And hence, the classical approach is to look at code for what it is, and then look at the static dependencies, and then document those dependencies. And how do we basically document these dependencies? The traditional approach is to basically build a graph, and this is what's called the task dependency graph. So here, nodes or the vertices in the graph represent tasks. Here, examples are tasks U and V, and the edges represent the dependency from one task to another task. So in this example, we have task V depending on task U, which means the data that is output by task U is needed, or at least some part of the data is at least needed as input to task V. So this arrow shows the direction of dependency, and this typically translates into a temporal dependency where task V has to typically wait for task U to complete. So here is a simple example of a task dependency graph. Let's say we want to really compute a maximum value in an array of size n. So I can write a pseudocode that looks like this. All I'm doing here is basically saying, here is a function called find max. It takes as input an array A, which is of size n initially, and then it takes two indices, B for begin, E for end. And if the begin is equal to n, that simply means that we are looking at the same index, so we simply return that value A of B. This is, in other words, the termination condition for your recursion. Otherwise, what we do is simply cut the array in half, basically locate your middle index, and then partition the problem into two subproblems, one containing the left half of the array and one containing the right half of the array, and then simply recursively call this function find max on each of these two halves. And if you record the max, the respective max values coming from these two recursive calls, and if we compare them and update the max, we will correspondingly report or output that max. So here is a simple example that shows, a cartoon that shows the execution pattern here. If we start off with an array of size 8, we essentially break it recursively at each step by cutting in half, and eventually get to the resolution of individual cells. And then we return the values, and here I have to essentially make a comparison comparing the minimum coming from the left half and the maximum coming from the left half to the maximum coming from the right half, and then record the new maximum and propagate that maximum upwards the tree until we find the maximum for the overall array. So if we assume that we have 4 processors, then what we could do essentially is we can assign jobs to these individual processors on who does what. And that's what defines this task dependency graph. This task dependency graph basically shows that the children at any given level need to be completed. Those tasks need to be completed before the parent can be completed. And respecting that dependency, if I have 4 processors, then I can basically assign P0 to the first group of two tasks, P1 to the next group of 2 tasks and so on. And in the next level, we can assign P0 and P1. In the following level, we have work only to assign to one process. Let's call it P0. So as you can really see here, when the number of tasks that we can execute in parallel is large, there is more concurrency, which is in the bottom of this computation tree here. And as the computation proceeds, the parallelism reduces. So in other words, we are able to use only less and less number of processes. So I'm going to show you some basic multi-threading example using OpenMP, and we covered OpenMP in a different lecture. There we use multi-threading using OpenMP for generally data parallel tasks and also for generating or for parallelizing for loops and so on. So in this lecture we will look at how to write code that does task parallelism, that implements task parallelism in the OpenMP framework. So I'll assume C syntax here, and the same thing will work for other languages such as Python. So the main construct that we'll use is what is the pragma OMP task. Okay, that's how you define a task that needs to happen at a single place, meaning at a single process. So the general construct is as follows. In a code, wherever you know there is a unit task, you encase that in this block, pragma OMP task. And if you happen to have dependency variables, meaning either variables which are needed by this task, these are the input variables to this task, or variables that are output by this task and needed by some other tasks, then you can document those dependencies using this depend construct, either depend in or depend out. So I'll show you some examples here. So let's look at a concrete example. So let us go to the code in your source repository and open tasks.c file. So the initial lines of this code is all it's doing really it's basically taking from the user the number of threads. So you can specify the command line what is the number of threads, and then calls this function OMP set num threads to really assign that many threads. So whenever we start an OpenMP region, a multi-threaded region, all those P threads will be active. Okay. So here is the main body of the program, which to do task parallelism, and this is just a small example. So here the goal of the program is I have this sentence, a quick brown fox jumps over a lazy dog. But let's assume that we break that into segments. There's one sentence broken into different segments. Each segment can be independently executed by a task. Let's assume that is our goal here. So for example, this task has been assigned to print just a quick word, and then this task is for brown, and this task is for fox. I've just put this outside because let's say that we want to print this particular printf this jumps over that class separately, and then we have lazy and the dog, right? So we have specified up to 4 tasks here in this case, and we have encased this in a pragma OMP parallel, which basically means that this entire region is a parallel region where all P threads will be active. They will all be executing all these lines. Okay. So let us now run this code. So to compile this code, what I do is I use a simple C compiler here. Let's call the executable as tasks. And then for OpenMP, you have to include a library. So I use that with a -f flag, -f OpenMP. And then here is the C file. So once it compiles, the usage of this task executable is we have to specify the number of threads. So let's go ahead and do that. Let's start with just one thread, for example. So here, this is the output, and it basically prints the sentence, although in a shuffled way. So now there's only one thread that's executing. However, the order in which these execute could get shuffled, and that's the whole point of essentially executing these in different tasks. What this is saying here is that to print this quick, you don't have to wait for you to print brown or any other word. So basically, we don't have to, if you want to print fox, you don't have to wait to print quick or brown. So essentially, we are willing to let go of the order, and as long as all the words are printed, we are fine. And so this is showing basically an expected behavior, and each time you run it, you may possibly get a different output, a different shuffled output. Now let's, out of curiosity, let's just run this on 2 threads instead of 1, and let's see what happens. And here something curious happens. Basically every word gets printed twice. So A, right, and jumps over is here, and jumps over appears again. And lazy dog here appears here, and lazy dog here, lazy dog also appears here. So everything gets printed twice, and why is that? So that is because you have a pragma OMP parallel. This is the parallel region. Both threads are executing, and both threads are actually executing all the lines here. So let's say our goal is still to output the entire sentence only once, regardless of the number of threads. So then what that means is we have to specify a separate line here, and that would be inside the parallel region. We say pragma OMP single. We basically create a new block here. What this block, the single block, basically does is it gives you a guarantee that all the statements here will be executed exactly once, just once, regardless of which thread executes it. Okay, so which means once a thread has picked a task to print this brown, no other thread will pick this. All right. So let's compile this code again, and let us run it with 2 threads, and now we see that the entire sentence is printed only once, just like it happened with a single thread, except the order of this printing might not be deterministic. It can vary when you run. So let's, out of curiosity, let's run it on 4 threads, for example. You still see the sentence being printed once. Of course, the order has changed here. So that is example number 1. Now let's look at another example. So I'm progressing here to, on the slides, to the task loops. Okay, so let's open that code. So essentially this is a very similar program, but here I'm taking in 2 arguments, which is the number of threads, and the other one is the number of iterations to execute. So once the user says execute that many iterations, I'm going to break that into a block. Let's say the user wants to execute n, uppercase n iterations, and if we have p number of threads, which means that I'm going to assign n over p batches of or blocks of iterations to each of the thread. That's, or to each of the task. So to do that, really what we will do is as follows. Okay, so let's say that I have a task here, pragma OMP task, 4 of them, and internally each of them are simply calling a simple function called f, and this function is really a function, 1-line function practically, which has this for loop. For I equals 0 to n times, do nothing. So it's going to take some time. to run this function depending on what the value of n is, right? Okay, now I have done everything else like before, like pragma MP parallel, and then we want to make sure that none of these tasks get executed by more than one thread, so we will do a single primitive here. And then I'm also timing it and then let's see what happens to the time. So I'm going to do a compilation first of tasks as before, this task loop, and minus or openmp fmp for the library. And then here is your loop. Okay, so the usage is here, let's say I give it only one thread to start with, and let's say I specify a small number of iterations. Maybe I like powers of 2, so let's go with 1024, approximately 1000. So as you can see, it has executed and it's showing 24 seconds. Also, this is going to be 240 or 24 microseconds. I'm sorry about that. Now let's do the same, execute the same number of iterations, but using 2 threads. The time actually went up, as you can see, right? And if you keep increasing the number of threads, again the time seems to be climbing up. The reason for this, of course, is that there are too few number of iterations here and too many threads, hence overhead takes over. So just keeping that in mind, let's again start, but give it a lot more work so that all the threads are kept busy. And I'm going to be generous here, and I'm going to give it a billion, set n equals billion, meaning a billion iterations with just one thread. So as it is executing, you have to understand that there's only one thread that enters this entire parallel region here, and then that thread essentially goes and executes in no particular order each of these 4 tasks. And each time it's going to run a billion, because n over p in this case is like the little n would also be billion. So we see 8 seconds here as the timing. So now let's keep the same number, a billion iterations, but make it 2 threads. Now we have 2 threads, and what you see now is the time has reduced. In fact, it has reduced by a factor of 4. Let's see why. So we have a billion iterations, that's uppercase n here. So what I'm doing in this code is basically I'm saying uppercase n, which is a billion, divided by 2 now, so half a billion each. Now I'm inputting half a billion as the workload to each of these 4 tasks. So in other words, there are 4 tasks to execute, each with half a billion workload. And I have 2 threads. Okay. So ideally what would happen is you have one thread take over this part of the task and another thread take over another task, and they all execute. And then another thread, whichever thread finishes first, will go pick up the next task, and then will execute block 3 and so on. Okay. So that seems to be happening, although we are getting a speed up that's more than what we expect. So we typically should expect only a speed up of factor 2 if we increase the number of threads from 1 to 2. Here actually I'm observing a speed up of factor 4. Okay, and that sometimes happens with these kinds of programs where everything is happening inside the memory and there could be some cache effects. So let's look at what happens when I increase the number of threads to 4, and in fact from 2 seconds it went down to 0.7 seconds almost. So it's about a factor of 3 improvement for an increase in the number of threads, which is only by a factor of 2. So again, more importantly, we are observing speed up here. So which means that the tasks are able to efficiently execute across these multiple processors that we have at our disposal. And then they're able to produce the output in a faster way. Okay. All right. So let's go back. So the other example that I wanted to show you was on how to use the depend class, and I'm just going to use the slide here, and we have the code. You can test it out. So let's say that I have a function, let's say I have a task which basically writes on to a variable called a, and then you use that variable a in a different task and use that for a value b. So these are essentially two dependent tasks. So in other words, the second task is dependent on the first one to finish. And that's why I've basically indicated this as depend in A, meaning it requires an input A, and so which means this task is producing an output A which will be used by this A, this task here. So in other words, if you execute this, then this task will act as a producer for variable A, and this task will act as a consumer for variable A, and the process effectively gets serialized here. You won't be able to see any meaningful speed up.